Oh, hi, everybody. Welcome to one of our final weeks of our annual HPC user training. And these last two sessions are all about all things GPU. And when the session is over, if you guys have been keeping up with the work, let us know about getting a CCR credit if you want. And you'll be able to keep your accounts for a good long while, like up to a year, so you can get back in there and practice some of the exercises. Today we're going to get two talks, one by Dr. Andreas Goetz, Andy Goetz. He'll talk about Introduction to GPU Computing, and Dr. Mahidhar Tatineni will talk about profiling using tools like Nsight. With that, I'll turn it over to Andy, you're first. They both are computational scientists and staff at the Supercomputing Center, by the way.
Right. Thank you, Mary. Let me try to share my screen. All right. Can you see the slide deck?
Yes.
Yep.
All right. Awesome. I just need to move the controls out of the way. All right. Okay. So thank you for the introduction and welcome everybody. So basically, we have the session today is split into two parts, and I'll take the introduction to GPU computing and programming, with a focus on expanse, and then before I hand it over to Mahidhar. Just a quick question: can you hear me clear?
Yes.
Awesome, thank you. Just to make sure that I'm loud enough. So we'll cover the following topics. I go briefly over a hardware overview. What is a GPU and why do we use GPUs? Briefly touch on GPU accelerated examples, and then show just very briefly, we don't have much time, how in principle you can program GPUs via libraries, CUDA. So that's going to be very abridged, of course, and then an introduction to OpenACC. And finally, I'll show you how to use SDSC expanse GPU nodes to compile and run GPU-enabled software. So if you think back about what a GPU is, it's really a specialized hardware. It's often called an accelerator because it accelerates certain types of applications. In this particular case, originally built for graphics rendering. And all this development has been driven by a huge gaming industry. There's lots of money involved. So that has been driving a lot of the development of GPUs. And originally, they had only fixed function pipelines for graphics rendering. But about a decade ago or so, modern GPUs have emerged that are programmable. So for general purpose, not only for graphics applications. So you can literally write just normal code that in familiar programming languages and execute that on GPUs. Because of the heritage and the way they are implemented, they have a simplified core design compared to CPUs with limited architectural features, for instance, like branch caches and so on, and a partially exposed memory hierarchy. And these are things, to actually program GPUs, you have to keep in mind and take into account. Now, the reason for there being such an interest in GPUs, I just want to have 2-3 slides about that, is, you're probably familiar with Moore's law that the transistor count in integrated circuits doubles about every 2 years. And that exponential growth still holds, right? So if you look here, the number of transistors is still increasing per chips. But if you look what happened around 2000, in the 2000s, what happened is, the clock frequency is leveling off. The single thread performance is, not growing exponentially anymore. What that basically means is you have to write parallel programs, because what happened is that instead of having faster processors, you effectively have processors that have more compute cores. And the extreme is graphics processing units, and they do have a significant advantage over CPUs in raw compute power. So if you look at these two plots, they plot the compute performance, the theoretical peak performance on the left in single precision, so-called 32-bit floating point numbers, and on the right in double precision, so 64-bit floating point performance. It's a little bit outdated. It's hard to make really fair comparisons with respect to floating point performance. But you can see that there is a big gap between, you know, what a state-of-the-art CPU could deliver and what a state-of-the-art GPU could deliver. And that holds both for NVIDIA hardware and AMD hardware. So the red one here is AMD hardware. So, you know, in principle, you have a much higher performance in terms of floating point performance out of a GPU. But that's not everything. In addition, the plot here on the left, it plots memory bandwidth, you know, so that's basically how much data you can move from memory to the CPU or the GPU processor and back. And you see a similarly large gap. So the memory bandwidth of the memory on GPUs is much higher compared to CPUs. And that is also very important because many of the algorithms nowadays that are in use are actually memory bandwidth bound. So it means, you know, your CPU or your GPUs actually could do more computations, but is actually waiting for the data to arrive or writing the data back to memory. And finally, you know, comparatively, CPU draws a little bit less power, so it depends on a little bit on the generation. But, you know, to be fair, you have to keep in mind how much power you're actually using when you're using a GPU or a CPU, because that's a considerable amount of the cost of doing actually running simulations. And that's a summary of a comparison of NVIDIA Tesla V100 cards. These are the cards actually that we have on SDSC Expanse. And that's a, you know, back then when these cards came out of state-of-the-art Intel 28-core CPUs. On Expanse, actually, we have 20-core Intel CPUs on the GPU nodes. I'll tell a little bit more about that later. But yeah, so what you basically see is that you get much higher floating point performance out of those GPUs. In addition, you know, the V100s introduced half precision, so that's 16-bit floats. That's typically not what you can use for numerical simulations. It's not a sufficiently high precision, but many of the machine learning applications, deep learning applications, so image classifications and similar things, you know, they can get away with half precision, or even other data structures that are now available in more modern GPUs. And the memory bandwidth is higher. And then this year's the PCI Express bandwidth, because, you know, the GPUs, they're actually sitting on, they're plugged into the motherboard. And, you know, when you start a program and you read data from disk, for instance, you have it in the CPU, you need to get it to the GPU first and or download it back from the GPU. And so that can be a bottleneck. And then the question is always, when you write code, or you use a code, you want that code to be portable, meaning, you know, you still want to use the code next year, maybe in the next supercomputer that comes out, or at home on your laptop, etc. And, you know, CPU code really is portable. I would say it's also true for GPU code. In particular, if you write it with OpenACC or OpenCL, but also CUDA is so widely used now, you know, I don't think there are any issues in terms of like code portability. Of course, if you write CUDA code that is specifically for targeted NVIDIA GPUs, then it runs only on NVIDIA GPUs. A very brief comparison that I like to make here is if you go back 20 years, the fastest computer in the world, the number one in the top 500, you know, cost approximately $110 million back then, so it would be much more nowadays. Filled an entire data center at Lawrence Livermore National Lab. SDSC Expanse, from the CPU nodes, we have an aggregate performance of 3.4 petaflops. The GPU nodes, there are 52 GPU nodes, each has 4 NVIDIA V100 GPUs, brings in an additional 1.6 petaflops in double precision, or 3.3 petaflops in single precision. And so you can see for $10 million hardware cost, we, you know, have an order of magnitude almost, you know, more compute performance. Or put differently, back in 2020, so GPUs are a little bit more expensive now because of supply chain issues, and you know, people have been using them a lot for cryptocurrency mining. But, you know, when those were launched, they cost about $700 each. So you could, for about $4,000 to $5,000 you could build a desktop machine at home that gets you 119 teraflops in single precision. But, you know, 119 teraflops performance, you know, when you compare that to what you had in a supercomputer 20 years ago. So you have a lot of computer power available nowadays. So it's really exciting times to live in, I would say. Then there's a wide range of GPU accelerated software nowadays. There's practically covering all fields, from bioinformatics to weather simulations, anything that you can think about, of course, medical imaging, etc. Were some of the earliest fields. The recent years, have seen an emergence of deep learning, and deep learning in particular has driven a lot of the GPU development and adoption and demand for GPUs over the last years, I would say. And so it's a specific type of machine learning approach where, machine learning, you use a predictive model based on some reference data. So you have some training data, you train a machine learning algorithm, and then, based on input data, you can make predictions, you can make an inference. And typically, you have to go through multiple training cycles until your model is converged, and then you can make reasonable predictions depending on the training, the training set data that you have available. And so one of those methods are these neural networks where you have an input layer, and then you see these are all interconnected. So if you write out the equations, literally those look like matrix multiplications, tensor operations. So that's why, you have like software that's called TensorFlow, for instance, Google's TensorFlow, and so on. And at the end, you have an output layer. And deep neural network just means, you have multiple, many of these layers. And there's like huge neural networks in which you literally have like hundreds of thousands of these nodes, and, with a corresponding large number of variables. And it also means that you need to do a lot of these matrix multiplications. And well, guess what? GPUs are just very, very efficient at doing these. In particular, 4x4 matrix algebra is used in 3D graphics. So they literally have had an inherent advantage for these type of applications. In addition, the hardware has been optimized for machine learning applications. So half precision, like I mentioned, can be used for many machine learning applications, at least when inference is used. And then the NVIDIA Volta architecture that we have from Expanse introduced tensor cores, which is really dedicated hardware that does these mixed precision matrix multiplications that you need to evaluate or go through these deep learning neural networks. And if you're interested in something like that, all the modern, most widely used machine learning frameworks that basically provide GPU support, like PyTorch and TensorFlow. PyTorch is in Python, of course, and I'm sure that next week we'll hear something about that when we are looking at Python support for GPUs. So that's pretty straightforward. You basically just have to tell PyTorch or TensorFlow that you want to run on a GPU as opposed to on a CPU. If you want to use multiple GPUs, it becomes a little bit more complicated, but at the end of the day, there's not much that you really have to program specifically for GPUs. If you do something else, like for instance, I do in my research is quantum chemistry. I have an example here, the open source quick code that we are developing. This is a book that's already a few years older, where we had contributors from different research groups who actually have been porting electronic structure calculations. So quantum mechanics applied to molecular systems or condensed phase material systems, and implemented this on GPUs. That becomes much more complicated. You really have to rewrite a lot of source code, but it can be quite successful because, as you see here, if you run on a CPU, we get a significant speed up running on a GPU. Or put differently, here is a scaling plot where these lines here show you the data points, basically the time to solution by increasing the number of compute cores, and that dotted line shows you that running on a single GPU is faster than our optimized CPU implementation running on what back then was an entire compute node, right? So significant speed up. And the same for molecular dynamics. That's another code that I've been involved in development, where you study interactions of molecules with a simplified force field representations, but these are typically run for many particles. So it's an n-body problem where you have like tens to hundreds of thousands or millions of atoms, and they all need to have the interactions computed over long time scales. We need to do millions of time steps, and at each time step we need to have compute all those interactions. And just, I don't want to talk much about that, but this is the Amber code in one of the performance examples where we have a cellulose strand in water that's approximately 400,000 atoms. And you can see on a single compute node here that was benchmarked back in, I guess, a few years back now. The maximum speed that we were getting is, is measured in how much simulation we can do per day, nanoseconds in the life of this molecule. That's a little over 2. And on a single GPU, even the cheap gaming GPUs, we are a factor of 10 faster, or that V100 units bounce a factor of 20 faster. So that enabled a lot of new science very cost effectively. Now, like I already mentioned, now we want to use GPUs, right? Because we can do our simulations faster, we use less power. And manager comes and tells you to rewrite your code, and then he comes back and says, well, why is your part taking so long? And it's not necessarily straightforward. It's not hard, but it's hard in the sense that you have to think about how to write data parallel algorithms. And so if you compare a GPU to a CPU, so this is a schematics of the real estate that you would have on a silicon chip. If you have the same surface area on a silicon chip, you'd have a few arithmetic logical units on a CPU to do the computation. So your compute cores, you have a lot of area on the chip dedicated to control, caching, complicated caching hardware, and so on. And on a GPU, as opposed to that, you have much more simplistic compute cores. And those are packaged into several multiprocessors. So similar to a modern CPU where you have many cores, you would have on a GPU many of these so-called multiprocessors, and each multiprocessor has multiple compute cores. These compute cores, they operate in lockstep, which means you need to program them in such a way, in a data parallel way, that they can do the same operation at the same time, just in different data elements. For instance, in a vector, when you do a vector addition, right? Then the GPU does vectorized load stores to memory, and you have to take care of the memory hierarchy. This is a very old Tesla T10 system. I believe that was probably the first, or one of the early, maybe not even this first data center node that was a compute node blade that was for sale by NVIDIA. And but that doesn't matter. I just put it up here because the basic architecture is still the same. And what you see here is what I was talking about. The GPU will have these multiprocessors, and each of those multiprocessors will have multiple compute cores, single precision and double precision compute cores, special function units. And each of those processors also has its own shared memory and data cache. And one thing to keep in mind is that it handles many more threads than processing cores. So when you write a CUDA program or a program for the GPUs, you can launch it, and you should launch it actually with many more threads than you have compute cores available in total. And the modern GPUs, they have thousands of compute cores. So the hardware characteristics, of course, change across GPU models and generations. And so when you look, for instance, the V100s, they have 80 of these multiprocessors. They have 64 compute cores per multiprocessor, so a total of 5,000 compute cores. And what that means is you need to write a program that is able to launch multiple of these 5,000, so maybe 50,000, on the order of tens of thousands of threads. So you need to be able to write massively parallel applications, right? Or to re-express a problem in a massive parallel fashion. And then there's, of course, NVIDIA and AMD. Those are different, but across different GPU models and generation, that's not a big issue. because it's similar to CPUs. You know, your code that you've written a year ago is going to compile for the next NVIDIA GPU the same way, and you should write it in such a way that it's not specific for a certain type of GPU architecture. So you never write a code with assumption about how many threads it uses. Instead, you use CUDA function calls to query the hardware configuration at runtime, and then you launch an appropriate number of threads for the available compute cores. And other things to keep in mind is if you can, you should avoid double precision, because the performance of single precision is higher. That's the same is also true for CPUs, of course, but it's easier actually to exploit that on GPUs. For machine learning applications, often you can work with half precision, or there are special data types now like bfloat16 or NVIDIA's TensorFloat data types that you can use. And I believe if you use some of these frameworks like PyTorch, that you know is pretty straightforward to use, as opposed to, say, for a scientific application that you write from scratch. When you do that, make sure that reduced precision does not lead to reduced accuracy in your simulations. That's just one thing to keep in mind, is very important. So if you want to program a GPU, there are different languages, and there's OpenCL, which is an industry standard. It works for NVIDIA and AMD GPUs. Probably the de facto standard for high performance codes is CUDA, for at least for NVIDIA GPUs. Works with C, C++, and Fortran. And it's proprietary. It works only for NVIDIA GPUs. However, there's something that's called HIP. I keep forgetting what the abbreviation stands for, heterogeneous something. So this is AMD solution with ROCm, which is the Radeon Open Compute platform. And it has a translator that translates CUDA code into HIP. And if you look at HIP, it has a syntax that's very similar to CUDA. So the translation is automatic, but you always need some, you know, after you've translated the code, you still need to, you know, debug it, et cetera, and optimize it. But you could write code in HIP, and, you know, under the hood, it will generate CUDA code or code for AMD's platform, and then you have C++ code that effectively runs on both NVIDIA and AMD GPUs. Then there's OpenACC. OpenACC are accelerator directives for NVIDIA and AMD, and they work with C, C++, and Fortran. And OpenMP also has accelerator directives, but at the moment they're not yet mature for GPUs, and so these two things, they might perhaps at some point merge. So, oops. Next slide. So let's talk about the NVIDIA GPU computing universe. So first of all, there are many libraries available. So high quality libraries. So there's like deep learning libraries, fast Fourier transforms, linear algebra, random number generators, sparse linear algebra, etc., etc. So there's a lot of libraries available. There's support for many programming languages. So I'll talk a little bit about C, C++, and Fortran. There's also Java and Python wrappers. So next week, we're going to hear about Python. And this, you know, works for all of NVIDIA's GPUs. So if you write code that runs on Expanse, it will run also on your laptop GPU if it's an NVIDIA GPU. So that's important to keep in mind. And this is the CUDA programming guide. It's actually a very good resource to have a look at and read. Now, if you actually want to develop CUDA code using NVIDIA's toolkits, there's a CUDA toolkit and software development kit, and it's free. So you can download this for free. It's always been free. It contains the CUDA C compiler that compiles CUDA code, and it contains a range of libraries that are very useful. Debugging tools and profiling tools that Mahidhar is going to talk about later. And there are many code samples included, which is also very helpful. And you get a lot of information here and can download the code. Now, if you are on Expanse, I always like to do a module purge and then module reset, just to make sure that I don't have accidentally something loaded that I wouldn't, modules loaded that I wouldn't want to be loaded. And then all you have to do is say module load CUDA and you'll get the CUDA toolkit. So this will currently load version 11.0, but there are also older toolkits available if that's something that you need or want to look at it. Then there is the NVIDIA HPC SDK, which is meant as a replacement for the CUDA toolkit. And it contains most of the CUDA toolkit, including CUDA compiler NVCC, right, that I mentioned before. The libraries that come in the CUDA toolkit, the debuggers and profilers. In addition, it does contain NVIDIA C, C++ and Fortran compilers. So they are called NV Fortran. So if you load that SDK, you have access to NV Fortran, NVC, this is the C compiler, and NVC++. And those compilers are basically what used to be the PGI compilers, because PGI was acquired by NVIDIA a few years ago. And you can get that for free from this link here. And again, similar to the CUDA toolkit, if you want to load that, you just say module load NV HPC. And that currently loads version 22.2, but there are older versions also available if you need that for some reason, for compatibility reasons, for instance. So with that, how do you actually use GPUs, assuming you have a software and you want that runs on CPUs, now you want to use GPUs. Like I mentioned, there are three ways, primary ways. You can use libraries, you can use OpenACC directives, or you can explicitly program this via CUDA, for instance. And if you use libraries, of course, that's ideal if you can do that, because you don't have to know much about programming, and you can just have a drop-in replacement. Typically, because all those libraries, they follow standard APIs. For instance, the BLAST libraries, the basic linear algebra systems. You can use Intel's MKL library or a vendor, or you can just download the source code of the CPU version of that, and the same way you can use the QBLAST libraries that are a direct replacement for that, and the code will run on the GPU. I'll just show you very briefly how that works in principle. And you want to use those because all those libraries are really high quality implementations that are highly tuned for the NVIDIA's GPUs. So use those if you can, and don't write your own matrix multiplication unless you want to learn how to do that. And that's, of course, a good thing to do, but not for applications that actually run production code. There is a huge list. You go to this link, you will see all the libraries that are available. Most of them are free and can just be downloaded for free. Right, so let's assume we have a call to a function. In this case, this is a BLAST function, basic linear algebra system. So SAXP SAXPY, this is a single precision function that does a times x plus y. So that's where the name comes from. And really all you have to do is to substitute that library call with an equivalent call to the CUDA library. So QBLAST SAXP. And then I told you have to manage memory, so you have to manage the data locality. You have to allocate memory on the GPU with CUDA malloc, copy data, forward and back to the GPU, and you can use functions that come with QBLAST as well, basically to copy and retrieve vectors, for instance, or matrices. And then all you have to do is you compile your code with NVCC and link it against the QBLAST library. So here's an example of SAXPY. So, we have input data is a constant A. There would be 2.0 here, and a vector or a linear array X and a linear array Y. And, you get as a result Y as A times X plus Y. And these are the strides that you have to provide to the BLAST function. And you would do this here for 1,000,000 elements, for instance. We want to do this on the GPU, we just call QBLAST SAXP. And now you see something that programmers sometimes do. They prefix the pointers here with or the variable names here with a D underscore to indicate that this must be a array or a variable that is allocated on a device, which is another name for the GPU. The device is attached to the CPU system. You have to do some setup for the QBLAS library, and with that handle here that you can pass through the QBLAS Saxby function. Then I said you have to allocate the memory on the GPU for those arrays here, dx and dy. This is just assuming, we're doing a single precision, so we have n data elements, so we allocate the corresponding amount of memory for the arrays dx and dy. And then we can use the QBLAS set vector functions that come with the QBLAS library. And what we do here is, again, so size of gives us the number of elements. N is the number of elements, and then what we want to do is we transfer basically the array X to the device, and we do the same for array Y. So these are arrays that are variables pointers to CPU memory, and these are pointers to GPU memory. We transfer the data to the GPU, and we call that function. It runs on the GPU, and when it's done, we copy the resulting data back. And then we call QBLAS free, so we free the memory that we have allocated on the GPU. And that's basically all. And this implementation is going to run on the GPU, and literally will work the same way for any other function or subroutine or function that you have, either C or Fortran. So let's take a very brief look at CUDA. So I still have a lot that I want to go through. I want to briefly touch CUDA, and I briefly want to touch OpenACC for you before we go to profiling. There's a lot of information at this link here. CUDA, there's C or C++ available actually. It's not only C, is a solution to run C or C++ seamlessly on GPUs. And it's modest extensions, but it still requires major rewriting of the code, right? So you don't need to learn a lot of syntax or new language, but you need to express all your algorithms in a highly data parallel fashion. And then there's a Fortran version that works with the Fortran group compilers or the NVIDIA Fortran compilers. I put up some links here, so you'll have those also in the slides about the NVIDIA HPC SDK, a CUDA C programming guide, there's a CUDA Fortran programming guide. There's many resources at this GPU Hackathons website. And these are already older books, but still, I think, good books to get started if you don't know anything about CUDA. Or there's certainly newer books, lots of resources online that you can find. And so any CUDA code will start with a CPU code. So you have a C code, for instance, right? That's a serial code that runs on the host. The host is the CPU. And at some point, you will reach a region in your program that you want to parallelize, and so you launch CUDA code. So you have to write this CUDA code, and what I've indicated here is you launch a so-called block of grid, a grid of blocks of threads. So in each of those threads block has many threads, and these blocks they then get automatically distributed by the CUDA runtime environment onto the different multiprocessors of your GPU. And then when the GPU is done, you get back to your host code. That can be serial, but it doesn't have to be serial. It could be an MPI code. It could be a threaded code as well, of course. And the processing flow is the same way like you've seen before with the library calls. So you have your host with its attached CPU and the attached memory, and then you have the GPU that's either sitting on the PCI Express bus or some other fancy interconnect that connects it to the CPU on the motherboard. And so you have to copy always the input data from the CPU to the GPU, which has its own memory here. And then you have to load the GPU program, you execute it, caching the data on the chip. You see here indicated the multiprocessors where the blocks of threads are now running on all of these many compute cores. And then when you're done, you copy the results from the GPU memory back to the CPU memory. And so I've been lying a little bit in a sense that you have to manually manage that memory. So you have the system memory, so the host memory and the GPU memory, the device memory. There's actually something in CUDA that's called CUDA Unified Memory, so you can use that in programming. That has a different API call in which you can just allocate an array, and the runtime under the hood will basically handle that for you. It's going to copy data to the GPU forth and back whenever it's required. However, it's primarily productivity feature, so when you're developing code, but once you get to performance optimizations, you still have to do that yourself because the memory copies still happen under the hood, and of course an automatic optimization is never as good as you can do that when you're profiling the code. Then I want to introduce a handful of terms. So if you start looking at CUDA, you will hear somebody talk about a kernel, and the kernel really is just a function. It's just source code in a function that can be executed on the GPU. And this source code operates in lockstep on the multiprocessors of the GPU. So it's going to be launched by many threads. All the threads are going to run the same kernel in what is called a SIMT fashion, so single instruction being executed by multiple threads. And that happens in multiples of 32, both on NVIDIA and AMD hardware actually. So the hardware works actually pretty similar. And a thread is the execution unit of a kernel with a given index, and then the CUDA runtime provides an index that is known to each thread at runtime, and you can use that basically to access via API function calls a certain subset of data. For instance, thread 0 operates on vector element 0, thread 1 operates on vector element 1, etc. And then the block is what I've been showing you before, is a group of these threads, and they're guaranteed to execute on the same multiprocessor. And by doing that, they can share and synchronize data via the shared memory. And you hear about a grid. That's just the number of blocks that are arranged into a so-called grid. And if you know the size of the grid and the size of the blocks, you know how many threads you have running in total, and that's all the information you need to compute strides, for instance, across arrays or one or multi-dimensional arrays. So these things basically they map to the GPU, and the warps within a thread block are executed simultaneously. So it's practically what I've just been telling you. Now we have these CUDA built-in variables that allow us to inspect for each thread. He knows what index it has. So there's like a griddim variable. There's a griddim.x.y.z. The .z is not used actually, but for blocks, it's used block ID X, Y, and Z. The reason for doing that is that, when you map a problem, so think about you have a vector, you have a one-dimensional problem, but if you have a matrix, or an image, pixels in an image, two-dimensional image, you might want to have an ID in X and Y dimension to make it easier for the programmer to index those. Or if you have volumetric data, if you do some computation, say on a three-dimensional grid, you might want to do a three-dimensional partitioning and indexing of your threads. And so in this example here is an example. So just pictorially, you'd have 72 threads running when you launch your kernels. You have like 6 blocks, and each block has 4 times 3 threads per block. Those are not real numbers that you would use in a real application. It's just because you can't put many more than this number of threads and blocks into a figure. And so I just want to show you, how that would work if you were to write a CUDA code. There's not enough time to actually teach that, but there's keywords like underscore global underscore that define a function that can be called from the CPU. So you can launch that function, you can launch that kernel. The CPU can tell, okay, now start running this kernel on the GPU, and it will execute on the GPU. And and then you can use these these built-in variables that I just was talking about within that kernel to compute an index, for instance, my thread index in this stride, and then I can do something like a vector addition. So this would be a simple vector addition kernel. And if we look a little bit further down here, the CUDA kernel launch specification, when it's launched actually in the CPU code, you tell it how many blocks and how many threads you're using. So these are the number of blocks in X, Y, and Z dimension and the number of threads. And with that, we'd launch many, many copies of this kernel that is running and executed in parallel on the GPU. Yeah, these are the other API function calls that handle device memory. And there's some more things to know about the memory hierarchy. You have the GPU memory. I told you it has a high memory bandwidth, but still it is comparatively slow. So whenever a thread requests data from global memory, it takes hundreds of clock cycles until that arrives. So it is comparatively slow. So the shared memory is actually sitting on the processor here, where this block of threads executes, and has the same latency as registers. So you really want to, for instance, use that shared memory to cache data on the chip when you write a program. And the constant memory is something that is helpful to, for instance, upload constants into the GPU memory, to the special type of memory. Let's say pi, you have, for instance, a natural constant, or or another constant like pi, and if all threads need access to the same constant, that will reduce significantly the memory bandwidth that is required to read those constants. And so what you want to do is, when you write a CUDA program, you want to avoid data transfers between the CPU and the GPU. You minimize access to the global memory because, like I said, this is the slowest part of the memory that you have, even though it's faster than RAM on a CPU. And so you can take advantage of fast shared memory by tiling data and partition it basically so that it fits into shared memory. And that's the same technologies that you would use in a CPU code to optimize it and do cache blocking effectively. And then you do the computations on that subset in the shared memory, which is much faster than accessing global memory. And finally, you write the data from shared memory back into global memory. So those are some techniques, and this is an example here about a matrix multiplication kernel that I'm actually not going to show you the code, but if you look into the CUDA samples, there's actually matrix multiplication implemented, and this is actually from the CUDA programming guide, and we'll explain that, so you can actually go into the CUDA programming guide and look at that. And there's a very simplified example where we assume that we have a fixed system size that is a multiple of the block size that we define when we launch the kernel, and that we would launch one thread for each element of the output data of a matrix multiplication, where you might multiply A times B equals C, right? And if you do that, so what you want to do is you have to load these tiles into your shared memory, and then you do the matrix multiplication in the same way as you would do a cache blocking, say in an OpenACC, or even not OpenACC, but in even a serial, implementation on CPU in the same way. In reality, of course, you want to use a highly optimized BLAS version, and there's the CUDA sample codes that I'll mention where you can find those that actually have both a cache block optimized implementation like this, handwritten, and a QBLAS call implementation, and you can play with that, and you'll see that the performance of QBLAS, of course, is much higher than even that optimized cache optimized implementation of the CUDA matrix multiplication kernel. So it's really hard to beat many years of software engineer optimized code. That's all I wanted to tell you about CUDA, because there's not more time. But it's a good background to understand a little bit about OpenACC and some pitfalls that you can run into when using OpenACC. The idea for OpenACC is that it's easy to make porting to GPUs code porting to GPU is quick and easy, and portable in the sense that, you know, also your CPU code still is running, because it's just like OpenMP. You use compiler directives, and so your underlying C, C++, or Fortran code will still work. And OpenACC is fully supported by the NVIDIA compilers, but also Cray compilers on Cray machines. Then there's like OpenMP, but as I said, it's not yet made sure for GPUs, so I wouldn't use it at this point in time, at least. There's the PGI Community Edition compilers. You can get those still from the NVIDIA website. They are free, and they will have the PGI Fortran C and C++ compilers. They work with OpenMP and OpenACC, both for CPU, and OpenACC for CPU and GPU. Profilers and libraries available. They're OpenACC code samples. And all you have to do is you say module load PGI on Expanse if you want to load it. Right. Or you could load the NVIDIA HPC SDK, like I mentioned before. And the way it works is, you know, I showed you previously the SAXP library example. This is a handwritten implementation that basically just does a for loop here, or here's the Fortran version on the right-hand side, that loops over each element in the vectors and just does this, multiplication and vector addition, right? And so all you'd have to do is you insert a pragma here, ACC kernels, and that just tells OpenACC to generate a parallel kernel for that, for the GPU. Or in Fortran, you'd have a corresponding block that is then enclosed by a corresponding end statement. So you have these directives, ACC directives or pragmas in C or C++. And we've just seen a kernels construct, and you can add certain clauses, with if conditions or async expressions or data clauses to it. So data clauses, what that means is, you can say copy in, copy out, create, present. And what that means, I've talked about the separate GPU and CPU memory earlier, right? And copy means, well, you have to allocate memory in the GPU and copy the data from the host to the GPU when entering that data region, right? And also copy the data back to the host, so back to the CPU when exiting the region. That's exactly what we needed to do in the SAXP example. We upload the data, X and Y, and when we're done, we download Y, just Y. So that means for X, you could say copy in, just copy the data to the memory, right? And so this can help, and sometimes you have to help the GPU and with these data clauses. And this is an example. I intend to upload some examples to the course website. They're not uploaded yet, but this is an example of a Jacobi iteration where you can solve basically the Laplace equation in 2 dimensions with that. Really, what you have to know about it is you have a 2-dimensional array. So you have a matrix A at time step k, and at the next time step, you compute the element ij here simply as the average of the values of the neighboring elements, I minus 1j, I plus 1j, and so forth. So that's all you need to know. This is how the source code looks like. So, well, this is what you know. So if you iterate this long enough, this will converge, right? To obviously. And so this is what you're doing. You have a while loop here that you let run either until you run out of a certain number of iterations that you set to a limit, or your tolerance, basically the difference between step k and step k plus 1 of the matrix elements is smaller than a given threshold that you set. Okay, so we're doing this while loop here. We iterate until we're converged or until we exceed the maximum number of iterations. And error is basically the threshold that we compute. And here we just loop through all our data elements, I and j, and we compute the new element just as a quarter, so the average of the neighboring data elements. And that's all that we need to do. And then we need to swap the, once this is done, we compute the error That's the maximum deviation for any of those elements between the input and the output matrix. And then we swap the input and the output matrix and we go on with our iterations, okay? Now, clearly this can be parallelized because in principle, you know, I can work independently on any of those elements ij. And so I want to do that. I just insert pragma ACC kernels and hope for the best. Then you can compile the code. You call it the PGI compiler, PGF90. If you use a Fortran code or PGCC, if you use C, and it will tell you what it does. You know, it generates these copy ins, copy out of you know, different arrays, A and A new that we've seen in the source code before. And then it generates here, it finds these parallelizable loops and it generates actually this parallel code for you. And you see something that you've seen before from what I told you about CUDA here, block IDX and thread IDX, right? So it generates basically a certain number of blocks with a certain number of threads within the blocks for these operations. And this is what you get. So this is actually compiled and executed on the Expanse GPU nodes. If you run it with OpenMP, so you get a certain speed up. So the speed up, you know, say going up to 8 threads is approximately 6 times speed up you get with a simple OpenMP implementation. OpenACC is super slow. So something really went wrong. So it's much slower than even running on a single CPU thread. So what went wrong? If we switch on profiling, Mahidhar will talk a little bit more about that. What's going to happen is you see that, oh, we reached a data region, we did data copy and transfers. That's 22 million microseconds, so that's 22.5 seconds, right? While here we have the compute region that is being launched, the kernel gets launched, we do a compute that took only 1.5 seconds. So literally we spent all the time transferring data between the host and the device. And the reason is that A and A new are resident on the host, and the compiler is not able to really understand that within that while loop, we actually never need to download the data during the iterations that we're doing, during the updates that we're doing, right? So we're doing all this copy forth and back between the CPU memory and the GPU memory, and that really kills our performance. So all we have to do now is outside of the while loop, we actually introduce a data region, and we tell the compiler to, at the beginning of the loop, to copy A to the GPU, not every time we hit the kernel and not download it afterwards, and create that anew on the GPU. Okay? So the input data is being copied in, and then once we are entirely done, at the very end of our Jacobi iterations, we'll download the data. And so if we do that, we recompile the code and we run it. Now we get a speed up that's about 7 times as fast as 8 threads, right? So that would be, I would say, a success. So we have code running on the GPU with minimal effort that is now about 7 times faster than the OpenMP code running on 8 CPU cores. And so, you know, there are various tricks to find and exploit parallelism in your code that holds not only for OpenACC, obviously also for CUDA if you do a handwritten implementation. And, you know, not everything can be done with OpenACC. So you'll have to be a little bit careful, but you know, often you can already speed up your code significantly with OpenACC. If you look for something like nested for loops, you just profile your code and you know where a lot of time is being spent, right? You need large loop counts to offset the GPU memory copy overhead. You know, the iterations of the loops must be independent of each other. Otherwise, you cannot parallelize it. You can help the compiler in C by using the restrict keyword, or you use there's a clause that's called independent to help the compiler if that is the case. And the compiler must be able to figure out sizes of the data regions too, and so you can use directives to explicitly control that. You should avoid pointer arithmetic because otherwise the compiler does not know if he can actually parallelize the code to avoid race conditions. And function calls within accelerated regions, so you have a pragma ACC kernels region, for instance, that must be inlineable, otherwise the compiler cannot, or OpenACC cannot parallelize that. Then you can use these compiler flags to learn, where time is being spent, so you can do some profiling effectively. Million pointer arithmetic, and then you can use inline function calls in the directive regions, and yeah, data regions. Basically, that's what I told you. To avoid excessive memory transfers, and this here contiguous memory. If your data is not contiguous in memory, that's gonna destroy the performance in memory access, right? I mean that's the same also for CPU code, but you feel that much more on the GPU accelerated code. And you can use conditional compilation with an OpenACC macro, which can be helpful. Now I filled my time, but I very briefly want to tell you how to access GPU nodes on Expanse before handing over to Mahidhar. You already heard about Expanse. We have 52 4-way GPU nodes. They're interconnected with NVLink, so they can talk to each other very fast for parallel computations across GPUs. So we have a total of 208 V100s. They're sitting in the bottom of the compute racks. If you were to go into the data center, the GPU nodes, they also have 40 CPU cores, so 2 × 20 core Intel Xeon processors. And the GPUs themselves, each of them has 32 GB of RAM. Now, if you log into Expanse, that's the login window that you get. You can use, you can write bash scripts and then, specify corresponding, make requests to get into corresponding partitions. So there's a GPU partition that will give you an entire node with 4 GPUs or GPUs shared, where you can request a single or multiple GPUs. If you don't need a full GPU node, how many GPUs you want to have, you specify with -- GPUs. And you could use SRAM, for example, to get access in an interactive session. So if I were to do that, just wait until resources are free, and then I would be logged in into a compute node. Once you are on a compute node, one thing to mention is, when you make requests, you should make the requests that are proportional to the number of available resources. So if you ask for a single V100, don't ask for more than 10 CPU cores, okay? And vice versa, and corresponding share of RAM, otherwise you get charged for more. And so if you are in a GPU node, like I said before, you can just, here on the right-hand side, load CUDA and PGI, or alternatively load NVIDIA HPC modules. If you want to use the CUDA sample and have compile those and have a look at those, they are available only for the CUDA Toolkit 10.2. They're not installed for the other toolkit versions, as far as I know. And so you can check for the NVIDIA CUDA compiler, MVCC -- version. If you have the module loaded, it should spit out information like this, or the PGI compiler, and will spit out the corresponding information. If you've logged in a GPU node, you can run NVIDIA SMI, that's the system management interface, and it will just give you information about the GPU. So you will see, for instance, if I have requested a single GPU here, GPUs equals 1 on a single node, I will see that I have 1 GPU available, and it's a V100 SXM2. You'll see also processes running. Of course, if I haven't launched anything, there's no process running on the GPU currently. So you shouldn't see any processes unless you start something and it's running on the GPU. And the CUDA Toolkit samples. So you load the version 10.2 CUDA/toolkit, and then you can copy this. So this is actually the path where the samples are. You could copy this into your home directory, for instance, into a directory, call it CUDA samples, and then once the copy operation is finished, you can go into this directory. And if you look at doing an ls command, you'll see there are multiple subdirectories, and you can look into the zero simple, for instance, has simple examples like the matrix multiplication. You can compile all of those just with a make command, or you can explicitly go into one of the examples, like in utilities, the _utilities directory, there's a device query example that actually does query information about the hardware. And if you compile that and then you run it, the device query command, it will give you a lot of information about the GPU, the GPU name, the driver runtime version, the number of multiprocessors and CUDA cores, the total number of CUDA cores, right, on the device and the GPU. And if you look into the corresponding source code, you'll see how these queries are actually done. The matrix multiplication example is in the _0_simple subdirectory. That's the one that I mentioned before. If you run that on the V100s, you will get about 3 teraflop of performance. Now, if you use the QBLAS version, there's a matrix small QBLAS subdirectory, and you compile that and then run it, you'll see you'll get more than double the performance, right? So the handwritten, still already optimized code, still much slower than the library that just tells you, use the library whenever you can. And then you cannot write OpenACC code or CUDA code, or if you have something else like Python, then you'll see how that works next week. And with that, I'm at the end. So I'd be happy. I don't know if I'm supposed to answer questions now, if there are any, or if you want to wait until Mahidhar is done with his part.
And you can take them now. I think it should be okay.
Okay. So if there are any questions, I don't know. Is there anything in the chat? Oops, sorry.
Maria, please feel free to unmute your mic to ask a question.
Thank you, Cindy. Great presentation. I have a couple of questions. Well, first, we know that there's a lot of programming environments available to better match the hardware that each company comes up with. Like we have the AMD GPUs and NVIDIA GPUs, and more are coming. And this difficult the task of the programmer to migrate their current programs to the new hardware. Do you think it would be possible one day to have one programming environment or language that is able to extract the most performance benefits from the hardware without having to tax the developer in terms of all the migration work that they have to do with new generation of a GPU or with a new vendor of a GPU?
Right. Yeah, that's a very good question, and it's very dear to my heart too, because there's nothing more frustrating than to optimize a code or work with a new, say, programming language, only to find out that 2 years later that code is not going to run anymore because maybe it's not supported, the vendor is out of business or whatever. So open standards are very important here. But I have to say that there is a conflict always between code that is performant on a hardware and code that is portable. So there's always a trade-off between that. It's very hard to get performance portable code. So meaning writing code that compiles for different hardware architectures and is actually also gives high performance in different hardware architectures. So yeah, it's hard to say. So either you have simple code and you can rely on libraries, and then it's not really much work. You just link against the corresponding libraries. You have a function called the matrix multiplication that can use Intel's library that then runs on their CPUs very efficiently, and on their GPUs when they are coming out. This was also developing GPUs for compute. Or you link against QBLAS or AMD's libraries and so on. But even there, AMD is much behind NVIDIA, for instance, with optimization of their own libraries. So depending on the functions you call, you get much lower performance on hardware that should be as fast as NVIDIA's GPU if you look at the data specs, at the specs and specifications. So in some sense, there is portability. Like I said, OpenACC helps with that. You write pragmas. They work actually. OpenACC code compiles also for CPUs. You can tell it instead of parallelizing onto the GPU, it's basically doing the same as OpenMP. And in some sense, OpenMP specifications are trying to integrate the OpenACC specifications. So this may all merge and become one thing. You also can write OpenCL code. I myself am not an OpenCL programmer. I've never programmed in OpenCL. That in principle also compiles for embedded hardware, CPUs, AMD GPUs, NVIDIA GPUs, and so forth. That said, it doesn't reach the same performance as CUDA. The reason is because it has not been optimized by NVIDIA for doing that. So there's always a trade-off. But I would highly suggest not to write code it's a waste of time, in my opinion, at least for production codes, to try to target architectures where you cannot be sure that they are going to stick around for a few years. I hope that answers the question.
Oh yeah, very well. Thank you so much.
Well, if there are no other questions, I would hand over to Mahidhar.
Andy.
Okay.
Let me.
So I'll stop sharing my screen. Sorry, I have this. Yeah, I think I got it.
Thanks. Let me see if I can pull up my presentation. I think I'll just share the whole desktop because I'll be switching between the presentation and the hands-on a little bit. All right, so let me get started. Let me move some things out of the way so I don't block myself. So the presentation looks good?
Yes.
Okay,
Yes.
great.
Yep. Great. Nice slide too, Mahi.
That's the original expand slide, right? So I'm going to be talking about the GPU profiling on expands. There are a few different ways you can do it. Andy already talked about the flag for PGI OpenACC to be able to do things. There are a lot of things from NVIDIA that also let you do profiling at various levels and details. So I'll talk about the options and so on. Excuse me. So few different things. I'll start with the simple command line kind of approach using nvprof. That just go over some of the options it has, and we'll use the same CUDA SDK examples that Andy was talking about to kind of illustrate the profiling process. And with nvprof, you can actually export the profile to a file and then open it up using a GUI based NVVP. So I'll just give you a snapshot of that, how to look at it. And then we'll also look at an OpenACC example, but using nvprof. So that's one set of things I want to cover. And then I'll look at the Nsight options. So there are two different things. There's Nsight systems and there's Nsight compute. I'll mainly talk about systems because we have the Nsight compute currently disabled. There's things that need to be done at a security level that we don't have right now. So that's disabled. So again, the Nsight, you have some command line things you can do, and then you can also use a GUI that you can download onto your desktop or laptop. So what you can do is use the CLI to create the the tracing or profiling information in a file and then bring it over to your home system and basically inspect it using the GUI. Again, we'll look at the same CUDA examples to kind of illustrate all of this. So let me. So the NVIDIA nvprof, it's a command line tool that basically lets you profile CUDA related activities. And the nice thing is it can look at both the CPU and GPU side. And you can get a display of the results on the console. And when I walk through some examples, you'll see the type of output you can get. Or as I said, you can save it and then view it using nvprof or nvvp, the visual profiler later. So there are several different options on both sides of the equation. So like you can look at the CUDA specific options. So there are kinds of events, metrics you can track, and the kernels and source level analysis, and you can do a dependency analysis to kind of see where your time is being spent and if there are any blockers or something is you're spending too much time in a particular area, so on. On the CPU side, again, you have a lot of different options in terms of the scope of what you want to profile, and also you can look at OpenACC and OpenMP2. And then with all of these, there are print and IO options so that you're not, you're getting something usable out of all this. And the number of options is quite a huge list, and I won't be able to go through all of them today. So I'm providing the link to the nvprof documentation, which has a lot of the stuff that I'll talk about, but a lot more details there. So the first thing you want to do is you can use NV, and I'm going to walk through this with the hands-on side of it. And for all the hands-on pieces that I'll talk about today, I uploaded the command list into the GitHub site. So you don't have to do that now. You can do that on your own time, but you can walk through and follow through all the commands that are there. It's a fairly simple setup, so you should be able to do that offline later. Few things. So you can actually query the kinds of things nvprof lets you look at. So for example, if you do nvprof -- query metrics, you will see all the available metrics that you can track, basically, like instructions per watt, like efficiency metrics and overheads and so on. There's a long list, right? So, and then later, like when you're doing the actual profiling, you can choose to do a subset of these things so that you can get the metrics that you're interested in. Similar things with the kind of query events. You can look at the active cycles, so the number of cycles a multiprocessor has at least one active warp, and some transactional stuff. There's a lot of options there also that you can look at by doing just those commands, the query commands. Now, profiling itself, you can do it in a very simple fashion by just running nvprof without any options. So here I'm showing what you get when you do that for the matrix multiply example that Andy was just talking about. So you'll see, and since this ran on expands, you're seeing it's picking up that it's a Volta with a particular compute capability. And you see the standard result that was there. But then after that, it actually gives you the profiling information of all the calls and where the time is being spent. So you can see quite a bit of time being spent in the mem copy from the host to the device and then device back to the host. A lot of time there. But then, yeah, you get quite a bit of detail. So just so we can look at some of these examples, I'm going to copy over that toolkit and then set up the profiling environment, and we'll run some cases. So we don't need to compile all the CUDA toolkit cases today. Just compile basically the simple matrix multiply and the one of the linear solver examples. So let me get out of my presentation window and go to my examples directory there. Now, one thing I want to say is that I already, okay, it's gone, but I used srun. Remember, Andy showed us the example basically srun command, and that, so I already ran that command, and that's how I have that interactive access to the node. And I'm going to basically look at all the command line options now. So let me actually change to this. So I'm just following the instructions that I uploaded. So let me just get that file up. So maybe I should just pull that over to the desktop. Can you see my browser okay?
Yes.
Okay.
Yeah.
So I'm just following through on these profile commands. So basically, I already did the srun with my particular account and did that. So let's start by just doing a reset and loading just the CUDA pieces. So that gives us the modules for the toolkit and the profiling pieces. And I already did this copy. So I'm going to go to the matrix multiply directory. Do a make clean and then do a make, and you can see the compiling it's doing. So it builds the matrix multiply, and then same thing in the directory for the linear solver. So I'll leave that alone for now, and then let's do a query, right? So first thing is I'm going to do a query metrics, because I just showed you just the first 2 or 3. I just wanted to show you what all. It's a long list of metrics that you can look at. So you can see the local load transactions, shared load transactions, and quite a bit of detail. Just wanted to show you that, because didn't want to put all of this into the presentation. But so you can track things at a pretty fine grain level in terms of metrics. And then similar thing for the events, and you can see the first few that I showed you, but then there's all these various types of instructions, events, and then tensor events and read write and so on. So there's quite a bit of detail in terms of what you can track. So let's go run the thing. So let's change to the, oops, I keep doing this. Change to the matrix multiply directory and run that nvprof command that I mentioned. So you can see now I just ran that and basically got the entire profiling information like we did before. But say now you want to look at a dependency analysis of where things are within all of these routines, where things are being spent, where time is being spent. You can run a dependency example. So I just followed through with the same test. So you'll with a CUDA linear solver test. So it's run the code, and you see the profiling result with all the calls for the various activities and kernels and how much time it takes. But then once you get to the dependency analysis, it actually looks at where things are being, where time is being spent. And you can actually figure out the particular routines from there. So it lets you basically dive in a little bit. So even though all of this is kind of from the command line, you're able to dig in a little bit into where things are, where time is being spent, and like I said, there are a lot more options, so you can kind of fine tune this a little bit. You can also go into a lot of detail in terms of the tracing to figure out how exactly these things are progressing. So then it will, so I'm going to run a GPU trace. So it's only going to show you the GPU side of things. So now you can see on the left, there's actually a timestamp, and then it's actually tracing exactly what's going on as you progress. So there's a timeline basically. So a lot more detail. Similar timeline you can do on the CPU side also. The other thing you might be interested in is to look at what is the system doing when all this is running, right? So there is an option. So I'm doing a GPU trace, but I'm also saying profile the system. So, so if I run that, you will see now there is a time, there's all the information with the timestamps, but there's also system information at the same time. So like you can see all these timestamps with what's happening on the system, what the clock was, what's the temperature, and so on. This is useful to find out if something goes wrong in terms of like, say you're hitting the thermal limits or something like that, and the clock basically drops. You will see that in the system level information. So it's useful to debug, and this does happen sometimes. And actually, I haven't seen it on Expanse, but on Comet, one time what happened was user had a really efficient code. So he was basically pushing the limits on what the GPU could deliver. And it turns out our fan speeds were not keeping up with what he was doing. So the GPU would get hot and you would see the throttling. So he lost performance. So he would run okay for 10 minutes and then start dropping in performance. And then it would kind of go up and down in terms of performance. So if you do a system profiling feature at the same time, you might be able to notice something like that. So notice all of this is right now at the command line level. So let me go back to the presentation, catch up to this point, and then I'll come back again to the. So let me go there. So we basically did this, right? We got a node. We set all the modules up. We saw how to get a timeline of activities on the GPU side. We can also get the timeline of all activities, basically along with the driver API calls that are invoked from the host. So that kind of gives you a chance to figure out, where in the code you are on the host side. And there's also an option to basically collect info on selected events, but that part of it is not active on Expanse now. Again, some of these options basically require the permissions on some of these GPU devices to be set to be more open than what we are comfortable from a security standpoint. That is why those are not supported. So I'll skip this because we just looked at that. So basically, and then we looked at the sampling of the power, clock, and thermal behavior of the GPU with the system profiling flag. So the -- system profiling on, and you can combine those two, so you can kind of get a timestamp overlay of what's going on. And then we looked at the dependency analysis. So the last bit I want to show is basically OpenACC profiling, but now using nvprof instead of the PGI flag that Andy had shown. So again, you can run nvprof on that code, and this is another code that you can copy over. It's in CM shared examples. So copy over that directory and you can run this. And then So you can do a summary and you can do a trace again, and you can basically use the OpenACC option so that it so that the profiler is aware that it's an OpenACC code. And finally, you can basically export this to a file that can be opened with NVPP, which is the visual profiler. So you can basically do an export file, -- export profile, and the name of that, and then do the same OpenACC trace and do a Laplace, which is the executable there. I'm not going to go into NVPP too much, but I can just show you a snapshot of it. Basically, it's the same information that we were looking at from all the text output, but in the visual form, it's a lot easier to look through, and you can click on the line numbers there and look at what part of the code you're at, and you can kind of dig a little bit deeper by just point and click instead of having to run with different options and then going back and looking at text files. Can get a little difficult from just a usability standpoint. So the NVPP is good in that sense. Going back to our command list here, so I'm just going to go to the OpenACC directory that I already copied, and just want to show you how it looks from a summary point of view. So this is actually running an OpenACC code, and the code is actually in that directory. So if you want to look at the code, it's a Laplace 2D code that you can see has these pragmas like Andy was talking about, basically the copy options there. So you can run the OpenACC profiling, and then again you can see where in the code you're spending time and get more information. So all of this is nice from a command line kind of perspective, but it gets a little difficult once you're looking at a very complicated code to be able to like parse through so much text data, right? It's not easy to spot things, bottlenecks or whatever, even though all the information might be in that trace. Going back and synchronizing, like if you see the timestamp and you're trying to synchronize all of that manually, it can take too much time. So that's kind of why NVIDIA has these tools that are the Nsight suite of tools that lets you basically do some of this in a graphical way and with a lot more control over how much detail you can get and look into basically the details in a easier way. And I can actually show you. So first thing is we'll reset, roll the toolkit, and now instead of the profiler, I'm basically using this Nsight path and changing to the directory. And now I'm saying I'm nsys profile. So this is a profiler that I'm running. And this is looking for CUDA and OS runtime stuff. And I'm just going to output this to a baseline file. And so if I do that, you'll see it'll run. And then it creates this. OK, it's going to say no because I already have this file. So let me delete that file and rerun this. So then it's going to create this basically report file that is basically put in the location that you requested. So I said baseline, so it's going to create this baseline.qdrep file. Now what you can do is take this file and move it onto the onto your laptop, and I've done that already. And then you can start looking at it using a GUI that Nsight GUI that you have on your laptop. So let me go to the Nsight page, Nsight slide. So again, this is a system-wide performance tool. It combines info from both the CPU and GPU side, and it gives a full system view of the code execution. So you can basically look at bottlenecks at various levels, basically, like GPU starvation or some unnecessary GPU synchronization, for example, or even on the CPU side, if you have some insufficient parallelization, then any inefficiencies in the memory access, data movement. And this can run both in command line, like we just ran, and graphical mode. And the command line run basically can export these report files, which you can send to your client machine and look at it. And there are a lot of tracing options, various different examples listed there, basically the CUDA, OpenGL, OpenACC, OpenMP, and MPI. Basically, you have OpenMPI and MPH options there. And you have basically CUDA and OS runtime backtrace options. And there are lots of info in the user guide. Again, too much to put into a short presentation, but you can go take a look there. And again, on expands, there are some limitations. So not everything that's listed on that NVIDIA side is going to work. But it's pretty clear if it doesn't work, it's going to say, oh, this particular thing is not enabled on your system. One thing I want to stress is it's best to download a copy onto your laptop that matches what we have installed so that you can use the GUI, because you can run it from expanse, but it's going to be really slow given all the graphical detail that is there. So I just went through this, so I'm going to skip that part. And we looked at how the file was created. So let's now look at one of the profiles that I already did. And I'm going to open up Nsight on my laptop now, and hopefully you can see it. Let me know if you don't see the Nsight systems thing, because I'm sharing the whole desktop, so hopefully it will show up. So everyone can see this?
Yes.
Okay, great. So I can start by basically looking at one of these files. So this is something that I had run before. So now you can see all the details here, and you can actually click through. And so I basically looked at the CUDA side of things, and I'm going to look at the kernels, and you can basically see where the time is being spent. And actually, the nice thing is you can actually zoom in into that piece if you want to. So if you highlight an area and then say filter and zoom in, you can actually zoom in, and then you get more detail of what's going on. So it's a lot easier to deal with, I'm going to get out of there. So if you hover over that, it will actually tell you grid and block level information, like what Andy was talking about, and basically a lot of detail. So obviously, it's a lot easier to track things in this way. And the other thing is you're also seeing the CPU side of things. So where things are being spent, time is being spent, and so on. So that obviously makes it easier to deal with finding things. Let me go back to the presentation. Okay. So we just did that, zoomed in, and you can see on the right all the kernels that were there. And this will match what we had with the nvprof. If you go back and look at it, roughly it'll match. So if you see the thing, there was 62.46 on this CSR Cholesky, I think, bi-level binary search free. So you can see it's basically the same one here, around 63%. I mean, it's a different run, so you'll have slight variations. But So it matches that info, except now it's graphical. You can zoom in, you can go look at things in a much easier fashion. And also remember, when I hover over a little piece, I can see what that particular piece of the code, how much time it took, and all kinds of information. And actually, you can look at different streams of things also. So it's a lot of ways you can look at it. So one thing I wanted to point out is an example Nsight systems process, basically, that kind of tells you how to use this. So this is just an example that NVIDIA has. So you can go look at that. The sample code is there. And what it does is it uses unified memory data movement and does like vector addition. So I think Andy mentioned in one of the slides that that's where like you can have the unified memory. So that's what they're using here. But what they did is they used like two different approaches for the data movement. So they did something with one case without prefetching the data and one with prefetching the data. So you can we can run these on Expanse and look at the profile. So when you look at something without the prefetch, you can see that the profile, there's a lot of transfer going on while the compute is going on. So the entire process is longer as a result of that. But if you run the same case without prefetch, then you see that there is some prefetch going on, and then the compute piece really becomes much faster because the data is already there now. So if this was a case like what Andy was showing, where you have lots of iterations going on once the data is there, then this will basically happen only once, and then after that you would have a lot of compute centric, 100% basically on the compute side of things. So, but you can see this visually now, basically, by changing those things and identifying the bottlenecks and so on. So those were the options. So there's I'm not going to go into an example with Nsight Compute. As I said, it's disabled on Expanse right now. But if you have, say, access to GPU on a cloud resource where you have, root access, or if you have, or you have access to a GPU where this level of access is enabled, then you can look at it. But basically, it's an interactive kernel profiler for CUDA applications. So what it lets you do is compare like performance metrics as you change things around in your application. It also goes into more detail in terms of the CUDA task profiling. It'll let you correlate with the source code, so that gives you more information. It also kind of gives you a roofline analysis, which tells you like, hey, how close am I getting to what can be achieved? So there is a nice example of the workflow out here, so you can take a look at that. But as I said, right now you can't do that on Expanse. So that was a very brief, quick look at all the profiling options. But just to summarize, there are lots of ways you can do this. We looked at the command line way using nvprof. So you can pretty much get all the info that you get from the GUI side, but you have to run these with various options and then correlate everything yourself, which is going to take a lot longer if you're trying to do it from text-based output. But it is possible to do all of it. You'll actually see the same level of output if you do the right flags. So there's also GUI-based options which let you do this kind of profiling. As I mentioned, some of these are limited with permission restrictions. We may enable some of these by putting a feature in Slurm so that if the GPU is exclusive, that is no one else is running on the GPU, then we might enable the next level of profiling so that the main concern is some of these flags are permissive that someone else running on the node can take a look at your what is going on. But if we have an exclusive node where you have all 4 GPUs to yourself, no one else is on the system, then we might be able to release some of those restrictions. So that's probably going to happen in the future, but not enabled right now. As I mentioned, nvprof is probably the simplest profiling tool, like command line, and we saw that it was quite easy to do the OpenACC profiling with just that extra flag there. Nsight Systems has both command line and GUI options. As I mentioned, you should use the command line option, write out the profile, and then do the GUI based work on your own machine, because that's a lot easier to deal with. Because all the zooming and all the like hovering that I was doing is going to be a lot slower if you're going to do that over the network remotely. So it's much easier if you do that locally. So I think I'll stop at this point and maybe take questions. We have quite a bit of time. Oh, you can.
Maria has her hand raised.
Yeah. Okay, go ahead.
So I thought the example you mentioned earlier that you mentioned was very interesting. The workload that was causing throttling in the system. Were you able? So the perception of the developer was, from his point of view, was that performance was being reduced after 10 minutes or so of running,
yeah.
right?
Yeah.
So but actually, even though it was his workload, it was something in the system that was precluding that program from running correctly. So could you, with these tools, from your developer perspective, debug that and reach that conclusion, or was the operator in the system that look at RAS events? Or
so technically we should be able to figure out as an end operator, but you know, it's often the problem is not the fact that we can or cannot do it, is like we have too much information, right? Like we are tracking actually a lot, like I should say that we do track a lot of the system metrics and they're all logged and everything, but we have like thousands of jobs every day. It's kind of hard to track what is actually going on in an automated fashion. There's a lot of work going on in this area where people look at system metrics and try to figure out bad jobs. Actually, I had a student who was trying to do that, not for the GPUs, but on the CPU side. But you could do it, but you probably need some kind of machine learning algorithm to at least pick up first level problems, right? Because we don't know if the clock dropped because of the code or something else happened, and something has to correlate that while the job's running. And I think it's not something feasible from a human point of view unless someone complains. So in this case, that's what happened, right? The user came back and came and said, hey, you know, I expect this performance because I know my code does this much efficiency and it works okay for 10 minutes, but it doesn't work later. So then we went back and looked at everything. But technically, if we were watching the thermals and the clocks, we probably can come to the same conclusion, but that would be picking one job out of thousands of jobs. So something has to be automated there to do some analysis at that level.
And it would depend on the other jobs running next door.
Yeah.
So
yeah, it's quite a difficult problem. It's not easy to figure out what is going on. Because sometimes, you know, the thing might be slower because like Marty said, there could be some other job that's a little memory intensive on the CPU side, and it's affecting the other job that's sharing.
If it's like on a shared node, it's like really hard.
It's hard to figure out, but it's a fair question to ask, and I'm pretty sure there are centers developing these sort of tools, like where they gather all this information and they try to pick things out of there. And I've seen papers of this, but it's quite a complicated effort to figure out.
I agree. The most I've seen is they store all the data, which is a slew of data, like you said. It's just too much.
Yeah.
But then they query within the window of time that the failure occurred, and that's how they try to correlate. But even doing that is just a big task, because the database can get really, really slow, and then it defeats the purpose.
Correct. Yeah.
I agree. It's a hard problem. Yeah.
So what we typically do is if a user comes back and says, oh, I didn't expect this to be slow, right? Or like if it's a code that we know should perform, like, a code like Amber, for example, there's a lot of published information. And if we run a benchmark and it's running slower than what it's supposed to be on a V100, we can go back and look at it. So, and that we can do, right? Like if something looks out of place and we get notified by a user or we notice it, then what we typically do is reserve the node and then run it, which is how we found this user's problem. Is we reserved the node, and then I was watching all the metrics while he was running and noticed that the clock was dropping, basically. And the other thing I want to say is some of these throttle events are logged in system logs. So you can go after the fact and look for those too. So
yeah, that's good that there's all those logs in the system. Yeah.
Yeah.
Thank you.
If we don't have any more questions, we can stop, I think.